Hi there everyone, and welcome to the first video setting up the material you need to know to do this project here at the end of chapter 15. The project is in a field of math known as apportionment theory. So these slides are an introduction to apportionment theory, the background knowledge you need before you get to the calculus and chapter 15. So the goal of these slides is to introduce you to the theory of fair representation, aka apportionment theory. No calculus here, all set up. So I'm going to go through this as quickly as possible just to get to the calculus, but there is quite a bit of vocabulary and setup involved. In particular, in these slides, I will do three things, and in this video, I'm going to do the first two. So I'm going to try to keep these videos short and sort of chopped up so that they are digestible. So in this video, I'll give you a general introduction to apportionment and then talk about it in the context of presidential primaries. And then in the next video, we'll go on to visualization of these things, which doesn't involve calculus, but does involve material from chapter 12, so that's nice. So this project kind of covers chapter 12 and chapter 15 with an emphasis on chapter 15. So let's start with the problem of apportionment. So this theory of mathematics traces its origins back to the U.S. Constitution. It is, as far as I know, the only field of math that can claim such a thing, that its birth was as a result of the U.S. Constitution. And Article 1, Section 2 says this: representatives to the U.S. House shall be apportioned among the several states, so on and so on, according to their respective numbers. So in other words, this is just a fancy 18th century way of saying if a state has P% of the country's population, that state should receive P% of seats in the U.S. House of Representatives. So there are 435 seats in the U.S. House. Missouri has 1.87% of the U.S. population. Therefore, Missouri is entitled to 1.87% of 435 is 8.1345. That's how many House seats Missouri should get. A House seat, of course, it represents a human being. You have to send a representative to fill a seat. So you cannot be given 8.1345. So I suppose that Missouri should receive 8 seats. And this seems kind of simple. It seems like there's not any interesting mathematics to be done here. Of course, if it were so simple, there'd be nothing to do here, right? This project wouldn't exist. So let me just show you the kind of complications that can arise. This is a small example, much smaller than the United States. So if problems arise here, then presumably problems arise with the United States and real countries, bigger countries. Okay, so suppose you have a country with 5 states, 100 seats in its house, has populations below. So if we were in class, I would have you guys do this. Apportion the 100 seats to the states in accordance with what the Constitution says. So you can do this if you would like. Let me just save you a bit of time. I just noticed I violated my own instruction here. I'm keeping 3 decimal places, but that's all right. I'm allowed to violate the rules. I make them. I can break them if I want to. You people must abide by them, though. That's a good parenting attitude if you want some parenting advice. Anyway, okay, so if you just figure out each state's percentage of the population and then multiply that by 100, then you will learn that A is entitled to 10.505 seats. This number here, by the way, is called A's fair share or quota. I'll make that more formal in a later slide. B is owed 24.512 seats. C is owed 30.690, and so on. So the thing is, if you do what you would like to do here, and I think what you would like to do is say, well, 10.505, I know what to do with that. I'll make that an 11. 24.5, I know what to do with that. Make that a 25. Make this a 31. Make this a 16. Make this a 19. If you do that, and you add 11 to 25 to 31, 16 to 19, you will get more than 100 seats. You will have given out more than 100 seats if you round like you want to round. You give out, I think, let's see. You give out 103 seats, I guess. So you go over by 3 seats. So the question is, well, what do you do then? And by the way, you can't just hand out 103 seats. So you can't just adjust that 100 to 103 based on the rounding you just did for reasons that I'm not going to get into. I'm going to control myself and not say everything I want to say. But just suffice it to say, for reasons, #reasons, you can't adjust that 100 to 103. So the question is, well, what do you do about this? Was rounding the thing to do in the first place? How do you handle these fractions? How should you divide up those 100 seats to the states based on this math in the, quote, correct way? That's the question. And it turns out that there is no such thing as a correct way. It depends on what you want, like what kind of methodology do you want and why do you want it? There is no sort of correct answer here, which actually kind of frustrates the CTI 105 students because we cover this material there. So you can start to approach this using whatever methodology you feel like. So there's sort of the general apportionment problem. What do you do with the fractions? So here's a general framework for what we're talking about. Every apportionment problem has these three things. States. So a state is a party having a stake in the apportionment. These can, of course, be actual states. They can also be people competing for things, country districts, whatever. The seats. So a seat is just something, it's a stand-in term for things that will be divvied up among the states. So the states could be competing for seats. Different hospitals can be competing for boxes of medical supplies, whatever. You can have children competing for pieces of candy, and for whatever reason the pieces of candy can't be cut up. You can have children competing for those, whatever. Then you have the populations themselves. So this is the set of positive numbers that are used as a basis for the apportionment of seats to the states. So these numbers can be literal population. They can represent time worked in the kitchen if you're trying to do a proportional allocation of candy, things like this. If you're rationing boxes of medical supplies, your populations might be the number of people in a given hospital or something, whatever. So every apportionment problem has these three basic things. You have states, which are apportioned seats in proportion to their population. That's what an apportionment problem is. And again, these are in quotes because they don't have to be literal states or literal seats. You might be competing for something besides a seat, as we will see later. So our first example showed, among other things, I guess, that solving apportionment problems is not simply a matter of rounding. If you try to just round, sometimes it might work out for you, but that example showed not always, If you could always just round and have it work out, then maybe this theory wouldn't exist, okay? So now let me march through some vocabulary here. So the standard quota, or I never use the term, I don't use the adjective standard because I don't like saying it every time. So I say quota or fair share of a given state is the exact fractional number of seats that state would get if fractions were allowed. So a state's quota is that state's percentage of the population multiplied by the number of house seats. That's how we got these numbers, 10.505 and so on. Upper and lower quotas. So once you calculate a lower quota just means round down to the nearest integer. So just shear off the fractional part. And also an upper quota, which means round up to the nearest integer. So like a 10.2 quota. Its lower quota will be 10. Its upper quota will be 11. So just, every fractional number, a number with a fraction, lives between two integers. So the lower integer is just, or lower quota is just the integer to the left, the lower one, and the upper quota is the integer just above it, to the right. Okay, so now let's look at a proposed solution to the apportionment problem. This is the first proposed solution due to Alexander Hamilton. I heard they made a musical about this method, and I'm a fan of mathematical musicals, so I'll have to check it out sometime. And here's what he proposed in 1792 for allocating seats in the U.S. House to states. He said what you should do is calculate each state's quota, then give each state their lower quota. So he says, look, in this example here, well, if A's quota is 10.505, shouldn't A get 10 seats at the very least? We're not going to give A 9 seats. That wouldn't be fair. Shouldn't B get 24 seats at the very least? And so on, right? So he says, look, lock in the 10, the 24, the 30, the 15, the 18. After you've done that, though, there are leftover seats. So what do you do with the leftover seats? You give them one at a time to the K seats left over, K states with the largest fractional parts. So you then look at the fractional parts of the quotas and look for the biggest. So for example here, 744 is the biggest fractional part. So state E would receive the first leftover seat. And then if there are still leftovers after that, state C would get the next leftover and so on. So in CTR 105, when we cover this, this is the method the students discover. This is the method that the students invent on their own. Oh, sorry about that. So it's a very natural method to invent, right? If you just ask people, what methodology would you use? They might not use the same language, but oftentimes they will come up with a Hamilton apportionment. So this is Alexander Hamilton's idea. again, the first proposed apportionment method from 1792. So let's look at an example. Here's a smaller example. So this small country has only 4 states with very small populations, 100 seats. Let's find the Hamilton apportionment for this. And as you move through the project you're going to do, I would suggest you use technology very liberally, so use it as much as possible. So of course, Hamilton's method, you can find a calculator for it. So I'm going to Google Hamilton's method calculator. Let me show you which one's the best. This second hit here, Math 130, Chapter 2, you click on that. And then there's a bunch of stuff. Sorry, this is so big. Hamilton method calculator, you click on, and that's what you want. So notice this calculator can handle up to 6 states. Can't handle any more, but that's fine. We won't need any more. So then you just type in these populations: 4994, 9500, 2500, 3500, and then you enter the number of seats. Oh, sorry. State E and State F aren't there, right? There's only 4 states. You enter the number of seats right here. It defaults to 100, so we don't have to change that this time. And then notice where all it shows you. It shows you every state's quota and their lower quota. So it shows you that after you allocate the lower quotas of 24, 46, 12, and 17, you've allocated 99 total. So there's 1 left over. And then it shows you where that 1 left over goes. It goes to State A by virtue of State A having the largest fractional parts. See, they show you the fractional parts. So State A sort of narrowly beat out State B for that last seat. So here's the Hamilton apportionment: 25, 46, 12, 17. So just use a calculator. We're going to use this calculator for other methods also because it shows you these quotas with the fractional parts. That's nice. It's useful. Okay, so anyway, here's the Hamilton apportionment: 25, 46, 12, 17. So now let me jiggle these populations a little bit. Suppose that 6 people move from B to A. So there's now a 5,000 here and 6 fewer here. Suppose that 60 of these people leave the country or die maybe. 10 of these people also leave the country. Let's find the Hamilton apportionment now. So I go back here and I say 6 more people here, 6 fewer people there, 2440, 3490. Okay, so now it shows you that when you do the lower quotas, you have handed out 98 seats. So there are 2 left over, and now those leftovers go to B and C. So 24, 47, 12, 17 is the apportionment now. And if you think about it, that's very strange. Okay, because State A, their population went up. State B, their population went down. And yet what happened? State A used to have 25, now they have 24. State B used to have 46, now they have 47. Okay, so Hamilton's method has some pathologies built into it. You can build sort of wacky examples like this, where even though my population went up and yours went down, you take a seat from me. So your representation improved, right? The more seats you have, the better for you. So my representation got worse, even though I have more people. Your representation got better, even though you have fewer people. It doesn't seem fair. So Hamilton's method has some pathologies built into it like this. So just a quick historical side note. So Hamilton's method was proposed. Congress passed it. Washington vetoed it, which is the first presidential veto in the country's history. So there's a little trivia fact for you, right? The first presidential veto was over a mathematical argument, essentially. What's the math we should use to allocate House seats to the states? So Thomas Jefferson had his own method he thought was better than Hamilton's, and he persuaded Washington to veto Hamilton's bill, and Congress subsequently passed a bill using Jefferson's method, which I'm not going to cover here for reasons. But anyway, this is all I'm sure covered in the Hamilton musical, right? On Disney Plus now, I'll check it out. After I make this video, I can't wait to see the math they rap about, you know. Everybody loves rapping about math. All you kids today love that. Okay, this is also a classical stuff, by the way, right? Dates back to the 1800s, 1792. In this classical context of apportioning House seats to states, much of the literature is focused on what's called the bias of a method. So when you're allocating House seats to states, it's best if you don't favor large population states over small population states, or vice versa. You know, so you wouldn't want to say, hey, California, you're so big, got so many people, here's some extra House seats beyond what the proportionality suggests you should get, you know. So like in this example here, it would be weird if we said, state B, you're so big. Let me give you like 50 seats and take away 3 from state C, right? It'd be weird to do that because like, why are you punishing the small states or vice versa? Why would you do that? Hamilton's method, to its credit, keeps things fairly proportional. It tries not to deviate too much from what the raw math says you should get. So this is worth putting in our back pocket here. So people care about bias of a method because bias in this context is seen as bad. It would be bad to say to Wyoming, screw you, you're so small. You get fewer seats now. Okay, so now let me move on to presidential primaries and show you a couple of methods there, and then I'll wrap this video up. So in a presidential primary that occurs in a given state, so think about the Iowa caucus, the New Hampshire primary, the Nevada primary, the Missouri primary, whatever, for either party, so this year there weren't really any Republican primaries because Trump was the incumbent, but there were, of course, a lot of interesting Democratic primaries. The candidates are competing for delegates, and these delegates then attend the national convention and vote for you at the convention. So like you're a Biden delegate or whoever else. I forget. It seems like it's so long ago, right? Who else? Elizabeth Warren delegate, right? Bernie Sanders delegate. And this is all very oversimplified, I should say, but it's not worth going into all the details. So basically, at the national convention, every single candidate has delegates who show up, and the person with the majority of delegates wins the nomination. So Joe Biden had the majority of delegates across all the state primaries, so then he wins the nomination. Now, in a given state primary, so in the Iowa caucus, in the New Hampshire primary, whatever, there are a certain number of delegates to be handed out, and they are awarded to candidates in proportion to their vote totals. Okay, so this is an apportionment problem where the context has changed, but it's the same idea. So classically, you think about House seats apportioned to states, proportional to population. In this context of delegates in the New Hampshire primary or whatever, you have delegates are given to presidential candidates in proportion to how many votes they got. Okay, so votes are playing the roles of population, delegates playing the role of House seats, and instead of a state, you have a human being, a presidential candidate, right? Now the presidential candidate is the party, the thing competing for something that must be proportionally allocated. So again, it's the exact same problem. You just make a terminology switch. House seats to delegates, states to candidates, and population to votes. And it turns out it's the same problem, same mathematical problem. So for notational purposes here, D will always be the number of delegates, N is the number of candidates, CI is candidate I, and I'm going to order them from biggest to smallest. So C1, that's the vote leader. So in like the South Carolina primary, Biden got the most votes, so he would be C1, and then I think Sanders got the second most or something, maybe Buttigieg, I don't remember, but that would be C2 and so on. So again, unless otherwise stated, they're ordered from biggest to smallest. Quota is denoted QI. Okay, so Hamilton's method could be used to apportion delegates to candidates, and many states do indeed use this. In fact, all Democratic primaries use Hamilton's method to apportion delegates to candidates in a state primary. The Republicans, though, do some other things. So there are other methods used, so let me show you some of those methods. So here's what Mississippi does. This is the state party of Mississippi for their state Republican primary. This is from 2016. Again, 2020, the Republican primary was boring. Right? Very few states even held elections for it because Trump was an incumbent, Okay, so their rules in 2016 said this: all fractional proportions of a delegate shall be rounded to the nearest whole number. Period. Stop. They then moved on to a next section. This is all they say about their math. Okay? So if you read these rule documents, and I'm sure all of you would love to do that, sounds very interesting, right? If you're like me and you've read the rule documents for every single state party from 2012 and 2016, you will come across sentences like this, where your first reaction should be, wait, what? We just saw an example at the beginning of these slides that showed you can't just round to the nearest whole number. It doesn't work like that, bruh. Sometimes you get too many delegates handed out. Sometimes you get too few delegates handed out if you do that. So this is not a complete method here, right? This is an incomplete method, but it's what their rules say. So if they run into a situation like what we've seen, where rounding doesn't work out for you, who knows what they do? They don't say. Presumably they just kind of hash it out in a committee meeting or something. Okay, so let me show you a real method now. This is used in places like New Hampshire, Alabama, New York, Vermont. again, on the Republican side, the Democrats all use Hamilton's method. The Republican state parties are allowed freedom. The Democratic state parties are not allowed freedom. The National Democratic Party stipulates Hamilton's method for every state primary. The Republican National Party does not stipulate a method. So the states are kind of free to invent their own methods. So the New York Republican Party, New Hampshire Republican Party invented this method. And it goes like this. Calculate everybody's quota and then round them like you want to. If that rounding worked out, you're done. However, maybe you gave out too many. So let D prime be the number of delegates that have been handed out after rounding. If D prime is less than the number of delegates available, then you have a surplus. You have not handed out enough, okay? Because D prime, the number of delegates you handed out, didn't quite match. It came in under the total number of delegates available. So you just calculate whatever the surplus is, there's your surplus, and you throw them all to the top candidate, C1. So this method is very much biased, you may notice, right? So you would not use this method for House seat apportionment because, again, you can't just tell California, hey, you're so big, here's some extra seats, because California hasn't earned their population the way that candidates earn their votes. So there's like a moral valence here that's absent from House seat apportionment. If you've earned the most votes, then here's a bonus for you, this method says. And that doesn't seem unfair, perhaps. On the other hand, what if you've overallocated? So you've rounded like normal, you've handed out too many delegates. What do you do then? Well, now this is the amount of delegates you have to take away to reach D. You punish the bottom candidate. So you go to the last place candidate and say, give me your delegates back, man. There are some caveats here. The last place candidate might not have any delegates. So then you go to the second to last place candidate, take delegates away from them, and so on. You keep doing that until you reach this total of D that you need. So again, if your rounding doesn't work out, you as the state party can't create more delegates or erase delegates. The delegate total is fixed, right? Capital D is fixed. So if you have surplus, you have to figure out what to do with them. Give them to C1. If you have the opposite of surplus, I don't know what that is, you've overallocated, you punish the bottom candidate. Okay, so let's look at a few examples before I show you one last quick method and then wrap this up. So here's an example. Let's find the NIE apportionment this time. D is 27. So again, even though this is a Hamilton's method calculator, because it shows you the quotas, I would use it for this. So these are ordered from biggest to smallest. 500 like this. Okay, so here are the quotas. So if you're using NIE, you round like normal. You try to. Okay, so this guy gets 46. That's the rounding. This guy gets 24. She gets 17. She gets 12. So in this case, if you round like normal, you just give lower quotas. So if you do that, if you round like normal, there's looks like one seat left over. So that would get thrown to candidate A, it looks like. Oops, I'm sorry. 27 seats, not 100 seats. I'm sorry. I see it defaults to 100. It tricked me. 27, okay. So sorry. 12.51, that would get rounded up to 13. 6.58 gets rounded up to 7. 4.6 gets rounded up to 5. And then 3.29 does get rounded to 3. So this will be like a 13, 7, 5, 3. Okay, so if you do that, you've actually, let's see. You try to hand out 13, 7, 5, 3. If you add that up, you get 28 delegates. Right? If you hand 13 to C1, 7 to C2, and so on, you've now handed out 28 delegates. So you have to now deal with that overallocation, and you do it by punishing the last place candidate. So you take one away from them. So now you do have indeed 27, and you got it by punishing the last place candidate. You say to them, you're a loser, man. Like, if you wanted more delegates, you shouldn't have come in last. If you didn't want to be punished like this, try not coming in last. Okay, let me show you one more here. So 9,500, 5,000, 3,800. And this time, I'm not going to fool myself again. The number of seats is 26. So again, the delegate count is playing the same rule as number of seats. So you slot that in there. Okay, this time, 11.87 would go to 12. 6.25 goes to 6. 4.75 goes to 5. 3.2 goes to 3. So if you try doing that, 12,653. You add that up, you get 26. So it worked out, you know? So you just stop here. You don't do any adjustments. You wanted to round like normal. You did round like normal, and you hit your target of 26. Okay, so let's look at one last one here. So now there are 100 seats, so I better type that in first. And now I have all of these populations: 14900, 11900, 95,000, 75500. You should also be doing this, right, to make sure you can do this calculator, use this calculator. Okay, so now this would become a 30, 24, 19, 15, 10. Everybody gets rounded down when you round like normal. So you would try rounding people down, but now you have an under allocation. And it turns out this adds up to 98. So oops, I handed out 98 delegates. I was supposed to hand out 100 delegates. What do I do with the surplus? Toss them to candidate 1 for coming in first. Okay, so here's another apportionment method, right? In contrast to Hamilton's method, which doesn't do this kind of like help the top candidate punish the bottom candidate like this. Okay, so let me quickly show you one other method. This is called the sequential upper quota method, or SUQ, an unfortunate acronym, but I don't know, it is what it is. I named this, by the way, without thinking about the acronym, but this is the most natural name, so what are you going to do? You know, the abbreviation is not supposed to have any sort of judgment involved. And this method was used in Kansas, Texas, Tennessee, and so on. So the way this one works is like this. Give the leader her upper quota, give the second place candidate her upper quota, so round up, round up, round up, and then you continue until you reach a candidate where you can no longer round them up because there's not enough delegates left. You give that candidate what's left, and then any subsequent candidate gets nothing. So basically what you're trying to do is round everybody up, but if you do that, you're going to hand out too many delegates. So at some point, the process breaks. You can no longer round people up, and so you stop. So I think I have the same example here, right? That was smart of me. Okay. So candidate A, you would round this up, even though it doesn't round up like normal, right? But this method says give upper quota. So you round up to the nearest integer. So this would be a 31. Round up to 25, round up to 20, round up to 16. And I should have been keeping track here. Okay, so 31 plus 25 plus 20. There are 24 delegates left, so I can round this person up to 16. So I'm going to hand out 16 to them. And now look, there's only 8 delegates left. So even though you might want to round candidate E up to 11, you cannot because there's not enough left. So you give candidate E 11 delegates. I'm sorry, you give candidate E 8 delegates. So here's what that apportionment looks like. So again, all 4 of these numbers were rounded up, even though the fractional parts would suggest rounding down. You're trying to boost the top candidates, right? So even if this person's quota was like 30.0001, you're basically saying, well, you came in first, so I'm going to boost you. And if this were 24.2, you came in second, good for you, boost you, so on. And so what you end up doing is punishing the people at the bottom because there's not enough left. Okay, so in summary here, let me wrap this video up. I think I took more time than I wanted to, but I don't know. I just wanted to get through that material, the methodology here. So to wrap this up, we can ask, would either of these methods work for house seat apportionment? And if we were in class, we would discuss this, but the answer, of course, is no, because they're too biased, right? Again, you can't tell whoever. Kansas, well, you're just such a small state. Sorry, man. So I'm going to give you way fewer delegates than the math would suggest. Or, hey, California, you're so big. Texas, you're so big. I'm going to give you way more delegates than the math might suggest. You can't do that. But with delegate apportionment, where you have candidates earning votes, that seems more natural. Doesn't seem so unfair. So arguably, these are appropriate. So I've shown you 4 methods, one of which is the incomplete one from Mississippi. Here are 3 real methods. There are other methods out there. But let's not overkill things, right? I've shown you the 3 interesting ones. Well, there are other interesting ones, but I've shown you 3 of them that are enough for us to deal with the calculus when we get there. So in the next video, I'll move on to some geometry, which we also need before we get to the calculus.